Hello everyone, today let's take a look at QP124. We suppose we flip a fair coin repeatedly, so it's asking us what is the expected number of flips required to get 10 heads in a row, and generalized to find the expected number of flips to get n heads in a row. And here, since our probabilities of flipping a heads or a tails are not going to change from flip to flip, and we could basically have an infinite number of flips before getting 10 heads, right? It could go on forever. We could basically best model this as a state diagram. Okay, obviously I'm going to start in the state where I have 0 heads flipped in a row, or the tails state, right? This is when I flip a tails. And then from this state, I have a 1/2 probability of flipping my first head, so I'll call this one 1h, and I have a 1/2 probability of flipping a tails, so then I'd go back to having the same 0 heads in a row, so 1/2 probability for each. Now from this state where I flipped 1 heads in a row, I have a 1/2 probability of flipping a tails, in which case I'd go back to the state where I flipped 0 heads in a row, and I have a 1/2 probability of flipping my second head, so I'll call that state 2h. Now from the state where I flipped 2 heads in a row, if I flip a tails with probability 1/2, well then I'll go back to the state where I have 0 heads in a row, and if I flip another heads with probability 1/2, well then I'm going to the state where I have 3 heads in a row. And it keeps going on like this, right? For 4 heads, I'm going to have a 1/2 probability of getting 4 heads from this state, and a 1/2 probability of going back to the 0 head state. So I have a 1/2 probability for this one as well. Similarly, I have a 1/2 probability going forward, a 1/2 probability going back to this 0 head state for basically every single state. So I'll just say ... all the way up to my n-1 head state. I'll come from my n-2 head state with 1/2 probability, and I'll go to the promised land, my n head state, which is what we want to get, right? We want to get to this state right here where we flipped n heads in a row. I have a 1/2 probability of doing that, and again, a 1/2 probability of going back to the 0 head state. So 1/2 probability for this as well, and once I'm in this state, I'm done, right? So we want to find the expected number of flips to get from this state right here to this state over here. So we're going to start with e sub 0 of x is what I'll call that. So starting from the state when I flip 0 heads in a row, I have a 1/2 probability of flipping a heads on my first go, in which case I'll flip it 1 times, and then I'll end up in this state. So I add on the expected number of flips to get to my end state from this state, which I'll call e sub 1 of x. Also, I have a 1/2 probability of flipping a tails on my first flip, in which case I'll flipped it 1 time, and then I'll find myself back in the same state that I started in, so back in e sub 0 of x. We can also just rewrite this. Basically, we can combine these like terms right here. These just sum up to 1, so we could just say instead 1 for my flip plus 1/2 times the expected probability from my first state plus 1/2 times the expected probability from the state that I started in. So plus 1/2 times this right here. Okay, so from my starting state, I flip the coin 1 time, then I have a 1/2 probability of advancing a state and a 1/2 probability of staying in the same state. So now let's calculate e sub 1 of x. So from the state where I have 1 heads in a row, I'm going to flip my coin again. I'm going to have a 1/2 probability of going to the state when I have 2 heads in a row, right? If I flip another heads, and a 1/2 probability of going back to the state when I have 0 heads in a row if I flip a tails. Same for e sub 2 of x. It's going to be the same idea. I'm going to flip my coin 1 time, have a 1/2 probability of advancing a state, so 1/2 times e sub 3 of x, and a 1/2 probability of going back to my original state when I have 0 heads in a row, e sub 0 of x. Now you can see the pattern is pretty obvious. If I have e sub k of x, it's just going to be equal to 1 plus 1/2 times e sub k plus 1 of x, the probability that I advance a state, plus 1/2 times e sub 0 of x, the probability that I flip a tails and go back to the state when I have 0 heads in a row. So now I keep going until I get to the state right before my final one, in which the expected value e sub n-1 of x, well, it's going to follow the same recurrence. It's going to be 1 plus 1/2 times e sub n of x plus 1/2 times e sub 0 of x. Now obviously e sub n of x, which is just the expected wait time from the state when we already have n heads to get n heads, is obviously just going to be 0, so this is going to be a 0 here, and this is just going to be 1 plus 1/2 times e sub 0 of x. Okay, now we can work backwards to try to find a pattern to get our final answer, which is going to be e sub 0 of x. Okay, so now by the same recurrence, this is what e sub n-2 of x is going to look like. We can just plug in this term right here. When I do that, you notice we get something like this down here. And now for simplicity, I'm just going to call this term c because it's going to keep on appearing, right? It's a constant that's kind of being added to every term. It's this one. So c is just comprised of the constant 1 and this constant 1/2 times e sub 0 of x, right? So basically what we can do is kind of rearrange this just for simplicity. I'm going to move this over here and move this 1 over here like so. And when I do that, this term right here is c, and then this term over here is c. So this is just basically 1/2 c plus c, or 3/2 c. Now you notice that for e sub n-3 of x, all we're going to do is plug in the term that we got previously. Now I'm using a c. You can see that in our general recurrence equation, this part right here is the c, so I'm just plugging in this term for this one. So e sub n minus 3 of x is equal to 1/2 times e sub n minus 2 of x, which was 3/2 c, and then all I'm going to do is just add on c for my extra term. And now when we simplify this, we're going to get 3/4 c plus basically 4/4 c, so this is just going to be 7/4 c. Now I can plug in that 7/4 c into my e sub n minus 4 of x equation. Maybe you can see the pattern now. I'm going to have 1/2 times 7/4 c plus c. So this right here is just equal to 15 on 8c. Maybe now you can really see the pattern. Let's just do one more e sub n minus 5 of x. I'm just going to take 1/2, plug in the term I got before, which was 15 on 8c, and then just add on c. So in this case, now I would get for this whole term right here, I'd get 15 on 16 in the middle, and then plus 16 on 16c right here. So this would give me 31 on 16c. So the pattern is I'm multiplying this term here on the bottom by 2 every single time, and this term here on the top, you notice, is basically a multiple of 2, but you subtract 1. Like this is 16 minus 1, this is 32 minus 1, this is 8 minus 1, this is 4 minus 1. So for e sub n minus m of x, well in this case when m was equal to 5, I had 31 and 16. So that's just basically going to be 2 to the power of m, right? 2 to the power of 5 is 32, and then I subtract 1, I get 31. And that's going to be divided by basically 2 to the power of m minus 1, right? When m was 5, we had 2 to the power of 4 on the bottom. When n was 4, we had 2 to the power of 3 on the bottom. So this is going to be multiplied by our constant c, and now you know that e sub n minus m of x, we found that it's equal to this over here. So we want e sub 0 of x. All we have to do is plug in m equals n, right? And then we'll get e sub 0 over here. So when I plug in m equals n into this equation over here, I get that e sub 0 of x is just going to be equal to 2 to the power of n minus 1 on 2 to the power of n minus 1 times c. And remember, c was just a replacement for our constant term of 1 plus 1/2 e sub 0 of x. And now we can solve for e sub 0 of x. So now this is just a bunch of algebra. So I'm just going to move to a new page because I'm running out of room here. So new page, made some new room. All I did here was just distribute this term inside of here to get to this. So once I subtract this term right here to the other side, all I've done is I've multiplied both sides up here by 2n, and I get this term, so I can use my common denominator of 2 to the power of n, right? And then all I do is I subtract off this term on top from here on the top. Now I can distribute this term inside of here. When I do that, I'm going to get 2 to the power of n times e sub 0 of x, and then a minus e sub 0 of x as well. Distribute this negative inside of here. I get negative 2 to the power of n times e sub 0 of x plus e sub 0 of x. You can see we get the nice cancellation here. Then I can multiply each side by 2 to the power of n to isolate e sub 0 of x. When I do that, I basically just get 2 to the power of n times 2 to the power of n minus 1 over 2 to the power of n minus 1. So this term's going to cancel right here with the first n minus 1 terms of this. So we can just rewrite this as 2 times 2 to the power of n minus 1, right? This would be in parentheses, actually. So that's the final answer. E sub 0 of x for a general n is just equal to 2 to the power of n plus 1 minus 2. When I distribute this 2 inside of here, right? This is our final answer. That was a super annoying recurrence to calculate, but we did it, and now it's asking us what is the expected number of flips to get 10 heads in a row. So basically n is equal to 10. When we plug in n equals 10 over here, all we get is 2 to the power of 11 minus 2. So 2 to the power of 11 is 2048 minus 2, we get 2046. So this is the expected number of flips required to get 10 heads in a row. You see it's quite a lot, and you can see also that as n increases, we're getting exponential growth in the number of flips required to see that many, right? And that definitely makes sense because we would expect exponential growth to get increasingly larger numbers of heads in a row.